I've got theorem 1 from your textbook up here on the board. It says that the two-sided limit of f of x is equal to L. And remember, by assigning a variable name to that, that's saying we're talking about a finite limit here. Although it turns out this is actually true for infinite limits as well, but that would require a separate statement. It looks like I have misspelled the word if, because I've spelled it with two F's. That's actually a mathematical symbol. It means if and only if. That can also be written as a two-way implication. So that says if this statement is true, then this statement over here is true, and it works the other way too. If this statement over here is true, then this statement over here is true. And the statement over here is that the two one-sided limits both exist and are the same finite number. Now, that's not too surprising, because when we've had a two-sided limit, we saw one way that that could fail to exist is if the one-sided limits were different. And certainly anytime a two-sided limit has existed, the two one-sided limits have been the same. This is actually a useful tool for certain types of functions. Let's suppose I want to take the limit as x goes to 0 of the absolute value of x over x. Now that's actually a function that we've seen before. In the very first section, when we were talking about derivatives or slopes of tangent lines, we got that this function here represented the slope of the secant line on the graph of the absolute value function. So this is not a graph of this function. This is a graph of the absolute value function. But if I calculate a secant line between the origin 0, 0 and a point x, comma, the absolute value of x, that's the slope that I'm going to get. Okay. Now, where this is helpful is because if I have the absolute value function, I can always write that piecewise. So the absolute value function, it's one symbol. I can think of that as one operation, but I can also think of it as giving me two different rules that I apply in two different circumstances. So I can say the absolute value of a number is just that number, and that would apply if x is bigger than or equal to 0. But if my number x is negative, then the absolute value isn't that number, it's the opposite of that number. So I would get the opposite of x if x is less than 0. Notice that negative sign does not mean that this is a negative quantity, because I know the absolute value can't spit out a negative. That negative sign is telling me that I'm getting the opposite of x, and I only apply that rule when x is a negative number. The opposite of a negative number will be positive. Okay, so often if I'm working with limits involving absolute value functions, at least if I'm looking at the place where the rule changes, which is right at 0, I need to rewrite my function piecewise. So I can do that. I can say the absolute value of x over x is going to be given by one of two rules. It will just be x over x, and I'll use that rule if x is bigger than 0. Now here I did not include 0, not because I can't include it for the top, because I certainly can, but because I've also got an x on the bottom, so my function is undefined if x is 0. But it would be the opposite of x over x if x is less than 0. And I can then simplify that even further if I want to, because as long as x isn't 0, that's going to simplify even further. So this is just going to be 1 if x is bigger than 0, and negative 1 if x is less than 0. So because my rules come in two different pieces, I can't really take the two-sided limit all at once, but I can take the one-sided limits. So I can say the limit as x approaches 0 from the left of the absolute value of x over x Well, if we're approaching 0 from the left, then x is representing a number smaller than 0, so we'd be using this rule. So this would be the limit as x approaches 0 from the left of -1, but the limit of a constant is just that constant. And then I can say the limit as x goes to 0 from the right of the absolute value of x over x. That's just the limit as x goes to 0 from the right of 1. Again, the limit of a constant is that constant. But now I can see these two one-sided limits are different. So I get to make this brilliant observation that -1 and 1 are different numbers. And then I can say, so the two-sided limit as x goes to 0 of the absolute value of x over x does not exist. So if I have a piecewise function, I may need to use this theorem, and rather than going to the two-sided limit all at once, I may need to do both one-sided limits in order to evaluate things. And that can occur if the function is given to you as a piecewise function. It can also occur if the function involves an absolute value, so that you can rewrite it as a piecewise function. What I'm going to do is put a limit up here on the board for you folks to try. Then I'm going to end the video. I suggest that you try this problem on your own before you watch the next video, and then in the next video we'll go over it together so you can check your work. So let's define f of x to equal x squared plus 1 if x is less than or equal to 5. Okay. And let's let it be, actually I don't want it to be 5 there. Let's do x squared plus 1 if x is less than or equal to 3. Okay. And let's let it be 3x plus 1 if x is less than 3. Okay. So, two different rules, and the rule changes at 3. Now, if I were evaluating the limit as x goes to 4 of f of x, I would say, well, 4, that's, whoops, I'm sorry, this should have been bigger than 3. I would have said 4 is bigger than 3, so at, and actually near 4, I'm using this rule. So I would just say this is the limit as x goes to 4 of 3x plus 1. That would be 3 times 4 plus 1. That would be 13. Okay. But what I want you to do is I want you to take the limit as x approaches 3 of f of x. So there, 3 is the point where the rule changes. So you're going to need to use that theorem that says that the two-sided limit exists if and only if the two one-sided limits both exist and are the same. So try that, and then in the next video we'll go over it together.